And yes, today I will be talking about reduced order modeling, I'll have a few slides detailing each of the keywords in this title. So, as Marie said, the first keyword is reduced order modeling. So, in our setting, we consider a time-dependent partial differential equation, like the one that you have written in the slide, in which we say that the solution U belongs to a Sobol space, which we call capital V, say for instance, H1 of omega, where omega is the spatial domain, and we have a possibly nonlinear operator, let's say A of U. What is it that you do when you want to write out a finite element solver for this problem? You write the corresponding variational formulation in space, and you get an equation like the one that is written in the middle of the slide. And after you have the variational formulation in space, you semi-discretize in time, for instance, by using an implicit method like backward differentiation formula. Then, in order to finish up with the discretization, you replace the space V with a finite dimensional counterpart that I will be calling VH, obtained by a further discretization in space by the finite element method, for instance. After this, you are able to solve the fully discrete system using your favorite finite element solver, for instance, Phoenix X. What about reduced order modeling? So, in reduced order modeling, you imagine that you go back to immediately after the third to last step. So you have just semi-discretized in time. But when carrying out the second to last step, you decide to use for the space discretization a different space. So you will end up using a Galerkin method on a different finite dimensional space that in the following I will be calling VR. What are the key differences between VR and VH? The first key difference is that VR is spanned by functions with global support, rather than the local support of the finite element functions in VH. And that the dimension R should ideally be very small, hence the name reduced. And that dimension R should remain roughly constant even when H goes to 0. So how is this VR constructed? It is constructed by compressing the time history of the solution you obtain from the finite element solver that you run in the previous slide. So in this talk, and mainly in my work, I use an algorithm which is called proper orthogonal decomposition. I won't be explaining to you what that is, but if you come from a linear algebra background, you know it surely as singular value decomposition, or if you come from data science, you know a very similar concept as principal component analysis. So then you call ROM, reduced order model, the resulting fully discrete system, and compute its solution numerically. For instance, in my simulations, I'm using the RBNXX library that I developed. And one of the questions that now one asks is, what is the loss of accuracy compared to the finite element solution? So the third part of the title is incompressible flows. So in my work, I mainly work on incompressible Navier-Stokes equation, in which we have an unknown velocity and an unknown pressure that satisfy a momentum equation, the first equation in the system, and the compressibility constraint, divergence of U equal to 0, the second equation in the system. What is so special about these incompressible flows when talking about ROMs? The kind of specialty is that, special item is that the pressure drops out of the ROM as soon as you are using an insub-stable solution when searching for the finite element solution UH-PH that you use while building the reduced order space VR. So in summary, in your ROM, you will only seek a reduced velocity, and you will not need any pressure to enforce the divergence constraint at the reduced order level. The first part of the title is regularized. Why is it that we need regularized models and when? So we need those in convection-dominated flows, and the typical scenario is that is the case in which the Reynolds number is very large. And In those cases, having a ROM can help overcome some computational challenges of the finite element method, especially for what concerns the space discretization part, in the sense that a convection-dominated flow may require a very fine grid in space, hence a very large finite element space VH. And then a ROM of small dimension R may result in much cheaper computations. Similarly, a ROM may help also in while carrying out the time stepping, in the sense that it will not compress the number of time steps, but at the very least, each time instance will be much cheaper to solve due to the previous item. However, I cannot promise that it's all easy, in the sense that ROM will have some computational challenges of its own, in the sense that in order to gain from the small dimension VR, we'd like to keep R as small as possible, but we can presume to have R arbitrarily small while keeping a good accuracy. And when discussing this concept for a finite element mesh, the CFD community calls this under-resolved. So calls a case in which the mesh size is too large to capture the solution accurately. So the CFD community has come up with, say, stabilization or regularization techniques for this under-resolved case. So the goal of what we are trying to do is to try to adapt some of these stabilization or regularization techniques to a ROM context when they were originally devised for a finite element context. So the first classical approach is due to Leray, which in the 30s of the previous century proposed to replace the nonlinear term in the Navier-Stokes equation, u dot grad u, with u bar. Sorry, there is the black box with the name of someone overlapping with the bar, but in there you should read u bar dot grad u, where u bar is a filtered velocity with the goal of increasing the solution regularity. So these regularization techniques has been used with remarkable success for instance, finite element methods in CFD. So the idea in paper number 2 by our collaborators was to adapt this, was to apply this in the context of reduced order modeling. So to find now two unknowns, the actual reduced velocity, UR, and a reduced order filtered velocity, U bar R, in the same space, VR times VR, such that the first equation is a slightly modified momentum equation, where the nonlinear term now has U bar R instead of UR. And the second equation is a definition of how this filtering occurs. So if you go back from the weak formulation to the strong one, you see that this filtering occurs basically with a Laplace operator scaled by delta square, where delta square is a filtering radius. So the advantage of this L-ROM over the standard Galerkin ROM is that this filtering can smooth out spurious oscillations. The disadvantage is that to achieve that, this results in a reduced order model that is typically over-diffusive. So to overcome this, together with my collaborators, in paper number 3 at the bottom of the slide, we employed a concept of approximate deconvolution that stems from signal processing and imaging. And the goal of this is to formally write the application of the computation of U bar as an operator G applied to U, where G is the filtering operator. So a reduced order model based on a deconvolution would replace again the nonlinear term in the momentum equation with a term that looks like G to the minus 1 applied to U bar dot grad U. However, in practice, you wouldn't really want to use G to the minus 1, for instance, because it would amplify noise. And instead, our proposal is to use an approximate deconvolution instead. So in terms of this approximate deconvolution, one simple idea is to use a Tikhonov regularization. So rather than inverting G, you invert G plus mu I and get out of this an approximately deconvolved velocity, UAD. if you plug all this into the Navier-Stokes equations, you get a system which becomes a system with 3 equations, where the third equation is how to compute approximately the convolved velocity out of the filtered velocity. So to compare our the 3 different reduced models, we started with a 2-dimensional case on a backward-facing step, and I will focus only on the plot on the left, in which on the horizontal axis you have time, on the vertical axis you have the kinetic energy. In black, there is the kinetic energy of the finite element solver. In red, there is the kinetic energy of the standard ROM, and you see that it is increasing when it shouldn't. In green, there is the kinetic energy of the first regularized ROM, the one by Leray. And when I told you it is over-diffusive, this is a confirmation of this in the sense that it dissipates kinetic energy when it shouldn't. In blue, there is our proposed ADL ROM, which, even though it's certainly not perfect, at the very least is the one that is closest to the black line. Then in one of the first slides, I also asked the question, is the result of this reduced order modeling as accurate as the underlying finite element solution? So in some work that we currently have in progress, we are trying to prove a convergence result in which, assuming that the finite element solution UH-PH, which is employed in the construction of the reduced Petty space VR, is obtained with Taylor-Root elements, let's say Pm plus 1 Pm for some integer m, and the BDF2 method in time, we are able to prove an error estimate for the L2 error at the finite time and an integral in time of the H1 semi-norm, where the bound on the right-hand side has the sum of 4 addends. The first 2 addends go as 0 as h to the 2m and delta t square. We have an addend that goes to 0 when r increases, and a final addend that doesn't go to 0, but remains constant as delta to the power 4. And I say that this doesn't go to 0 in the sense that delta square, we cannot expect this to go to 0, otherwise there would be no regularity. So to sum up, I discussed some peculiarities of ROM for convection-dominated incompressible flows. The next step would be to apply this to parametric problems. And finally, I acknowledge my funding through the ARIA and the Romeo projects.